Here are solutions to homework set number 1 for ECE 463-663 Modern Control. This homework set looks at Laplace transforms and dominant poles. The first problem is kind of a Jeopardy question. Here's the answer. What's the question? If I had the step response, what's the transfer function? Now back in signals, it's given the transfer function, find the step response. This is going backwards. On the first problem, I can kind of see that there's no oscillations, just a nice simple exponential rise that tells me right away this has a real pole. So that's roughly what the transfer function looks like. For this, I need to come up with two parameters from this graph to find my two unknowns. One of them is the 2% settling time. It's right around here. What it is exactly is kind of hard to say. If I say maybe 0.7, then B is 4 over 0.7. Now where the number 4 comes from is I have 2%, 0.02, is e to the minus bt. Taking the log, the reason for 2% is back in the days of slide rules, logs were hard to find. 0.02 has a nice logarithm. It's minus 4 for anti-log. Minus 4 is minus bt, giving you t is 4 over b, or b is 4 over t. That gives you B. To find A, look at the DC gain. The DC gain is about 22. So G of S, as S goes to 0, should be 22. Solve for A. So put that all together. I solve for B. B is about 5.71. Solve for A. A is 125. This is the transfer function. Now your answer is going to vary. Again, the 2% settling time is kind of hard to read off the graph. It's somewhere in this region. But it should be, kind of same idea, something like that. 4, 5, 6, 7, somewhere around there for the pole. Problem 2. If I have a system that oscillates, now find the step response, or here's the step response, now find the transfer function. In this case, I have complex poles. That's the complex part of the pole that causes the oscillation. So I know right away I've got a pole with a real part and a complex part. And in this class, if you have a complex pole, you have to have its complex conjugate. That's not true in communication circuits, but that's a different class. For this class, poles are always in complex conjugate pairs. So I need to pull 3 pieces of information off this graph. One of them is the settling time. So it looks like the 2% settling time is somewhere around here. If I say 450 milliseconds, ballpark, I know that B is 4 over the settling time. To find C, that's the frequency of oscillation. To get C, I've got 1 cycle, 2 cycles, 3 cycles. Let's grab this one. I've got 2 cycles in 0.32 seconds. That gives you hertz. Anything English is wrong, so multiply by 2 pi to give you radians per second. Finally, the third term, to get A, I will look at the DC gain. DC gain is about 1.2. So this, as S goes to 0, should be 1.2. Solve for A. So doing that, I get the real part of the pole, 8.89, the complex part of the pole, 39.89, ballpark, and to find the gain on top, pick it so that the DC gain is 1.2. Solving, I get this is my transfer function. And again, your answers are going to vary, but be something kind of like this. Problem 3. On the third problem, given a transfer function, what's the differential equation? Well, to do that, I first multiply out the polynomial. In MATLAB, I can do that by saying I've got poles at minus 1.5, minus 5, minus 7. What polynomial has those roots? And here's the answer, meaning s cubed plus 13.5s squared plus 53s plus 52.5. So multiplying it out gives me this function. Now cross multiply and note that sy means the derivative of y. S cubed is the third derivative, second derivative, first derivative, y, and x. So that's the differential equation. that corresponds to that transfer function. So anytime you see a transfer function in S, think differential equation. Problem 4. Given that transfer function, find the output when x is a sine wave. So this is a phasor type problem. This is the gain everywhere. All I care about is what's the gain at 2 radians per second. So evaluate at s equals j2 times the input at 2 radians per second. In phasor form, that's 3 minus j7, the real part's cosine, minus j is sine. Multiply it all out, and you get a complex number. Another way to do that, in MATLAB, I can input the system g of s into MATLAB. S is j2, x is 3 minus 7j. Then the output is g of s at s equals j2 times x, get the same answer. What that means is the real part's cosine minus j is sine, so there's y of t. Problem 5 is find the output when x is u of t. Now the difference between 5 and 4 is at t equals 0, I had a sine wave. If this is true for all time, I don't care about the transient, I just want steady state. That's phasors. In problem 5, what I have is at t equals 0, nothing happened before t equals 0, the output happened after t equals 0. So there's my step input. When you have it turning on at t equals 0, that's Laplace transforms rather than phasors. So to solve this one, I substitute. Take the Laplace transform of x, plug it in. That's the Laplace transform of y. Now this isn't in my lookup table, so what I'm going to do is use partial fractions. I know I can express y in this form, partial fractions, just have to find a, b, c, d. A couple ways of doing that. You can use the cover-up method to find a, cover up this term, and multiply by, or evaluate at s equals minus 1.5. In MATLAB, what I'm going to do is input y at s equals minus 1.5 plus epsilon. Evaluate g of s at that point times s plus 1.5. What that does is that cancels out this term, basically the cover-up method, and I get a. I need to perturb that by epsilon, because otherwise I get 0 over 0. MATLAB doesn't like that. So move this just a hair away from minus 1.5 to avoid a 0 over 0. Likewise, to find b, evaluate at s equals minus 5 plus epsilon. I get 5.71. At s equals minus 7, s equals 0. So here's the partial fraction expansion. What that means is this term is minus 6.9 e to the minus 1.5t plus 5.7 e to the minus 5t minus 2.5 e to the minus 7t plus 3.8 for time positive. Problem 6 is here's a third order system. Give me a first order system that has almost the same step response. So here's where we use the idea of a dominant pole. This is the slowest pole, that's the dominant pole. So when I come up with a model, I want to keep the dominant pole. That dominates the response, it's really important. And then pick A to match the DC gain. So the DC gain of g of s is 3.8. Pick A so that my first order model also has a gain of 3.8. Solving for A, that's my first order model. I can check. Let's take the third order system, take the first order system, find the step response of the third order system, find the step response of the first order system, plot the two together, and here's what I get. This is the first order approximation, there's the third order system. I've got the same DC gain, same shape, same settling time. It's almost the same system. The two poles I ignored do have an impact. There's a delay in the system. So a slightly better model that is sometimes used is a first order system plus a delay. And just by using trial and error, I can sit there and see how much the delay is. It looks like about 0.37 seconds. So here's the third order system in blue. Here's the first order system with a delay. That's probably a better model. So a better model for the system is your plant plus a delay. That's one of the reasons we have delays in some of our models. Sometimes we'll include a delay, sometimes we won't. The problem with the delay is I don't have poles and zeros, and in techniques that we'll be using later on, like root locus, I don't know what to do with a delay. So oftentimes we ignore the delay just because it doesn't fit our tools. But it's a little bit better model if I do include it. So that is homework set number 1 for 463-663 Modern Control.